Okay. Why is that still on? Okay. There we go. Okay. So, today we are going to continue with chapter 11. I've got some of the material worked out on the board already, and from the last section that I did this with, and I didn't see the purpose in denying you guys benefit of being able to look at that material, so won't be able to step through what's already on the board together, rather than waiting on me to write it all out by hand again. Today we're going to talk a bit about calorimetry and phase change, two things that I hope at least sound familiar from previous courses that we've had. With any luck, this will be review. If not, I'll still make sure to go through it, go through everything for you guys. So, before we get started, any questions, concerns, comments about anything at all? Okay. Brief reminder, I know I probably say this every single time, but I don't always remember. Chapter 10, homework and quiz are currently due Tuesday the 9th at midnight, which means we can come in and during class on that day, ask questions, make sure everyone's on stable ground with all the assignments, and then it'll be due that midnight. And then we'll shift to one assignment per week from there, but they'll always be due Tuesday at midnight so we can have the class day. Labs this week went very well. We're going to continue into next week. In general, we'll have a lab every week unless I say otherwise, reasons I might say otherwise, including it being a test week or including there being some sort of an event that week that cancels class on one day of all the lab days. I just don't want to bother with one being ahead of the others. So I know I'll have at least one of those weeks within this term. And with all that said, unless you guys have anything specific on your minds, let's go ahead and get started so we can all get on to our Friday and our weekend. So, past day or two, and in lab, we examined, or re-examined for most of us, this statement, Q equals MC delta T, referring to specifically how much thermal energy it takes to change the temperature of a specific amount of a specific type of thing. In general, the higher the specific heat of any given material is, the more thermal energy it needs to change temperature. Water has one of the highest ones, ergo, water takes a lot of time and energy in order to heat it up or cool it down. The thing about one of the things about thermal energy, not just the thing, is that if one object gains thermal energy, some other object has to lose the same amount. This is due to the law of conservation of energy. Energy cannot be created or destroyed. Therefore, if thermal energy leaves one thing, it has to go somewhere else. Now, very often, thermal energy will enter the environment around us, and it'll become very hard to track, because if you're doing an experiment, it's hard to figure out how much thermal energy leached into the air or into the equipment instead of whatever you're hoping will end up in. But in certain ideal situations, we can assume that it's all going to be funneled straight from one place to the other. This is pretty easy in conditions where one of the objects is directly touching the other, and they are the only two major things happening in the situation. So this act, this type of question is called calorimetry, where you are tracking thermal energy transfer very specifically from one object to another. And who here has not seen the word calorimetry before? Okay. Good. So this type of question will usually involve one object losing thermal energy and one object gaining it. So as a sample, we're going to do a little bit of blacksmithing. and we're going to drop hot metal into cold water to cool it back down after we have performed our experiment or our forging upon it. We're going to drop 50 grams of copper. This copper starts at 120 degrees Celsius into 1 liter of water that starts at 21 degrees Celsius. What is the final temperature, I should specify, of both objects combined? The word for this is going to be over here. So this bit right here is everything related to this particular question. Whenever two objects are in thermal contact, which usually just means whenever two objects are touching, they're going to try to reach thermal equilibrium, which is just to say they want to be at the same temperature as each other. Whenever two things touch, the goal of that interaction is to normalize the temperature of both objects. So both of these things interacting, the water and the metal, wants to end up at the same final temperature. So we list out the things that we know and we don't know. We're dealing with copper and water, which have their own specific heats, as listed on our table in our notes. We know the mass of the copper, 50 grams, and all of our formulas are designed to take kilograms, so we're going to convert that to 0.05 grams. We're told that the volume of water, and uniquely, 1 liter of water has a mass of 1 kilogram. So keep that in mind here, and keep that in mind if you are ever told volume of water in the future. That will tell you what its mass is. Yes?
Is 1 milliliter 1 gram?
Yes, for water.
Yeah.
There's probably a few things with the same density, but water's the only one I can think of off the top of my head. I think it's 1,000 kilograms per meter cube, because 1 meter cube is a lot. Next, we are told the starting temperatures of both materials, they're going to end at the same final temperature. This type of calorimetry question shows up pretty regularly, where you're trying to figure out the final end result temperature of two objects that are in thermal contact. It's also probably the trickier kind, because you've got one variable in two different places that we have to combine and rectify. Any questions reading my chicken scratch?
Is the initial temperature under the copper, is that where?
Yes. I realize my notes are a little inconsistent here. Yes, that's supposed to be a W for water. For some reason it has a tail. And I apologize for the inconsistency. I've been writing H2O. I don't know why I switched.
Not a lot of markers.
I have lots of them. I just can't find the one I was using yesterday. There it is. All right, a little more inconsistency there. So, they're touching, thermal energy will transfer from one into the other. So we're going to look at our calorimetry question. When I start doing the math, I prefer to write it like this. In the notes, just a refresher, what do the brackets on either side of each term mean? Very good. And that's there because since one object is losing thermal energy, Q is going to be negative on that side. Meanwhile, one object is gaining thermal energy, so Q should be positive on that side. Even if the numbers match, technically speaking, they're not equal if the signs are different. So there'll be absolute value on there to equalize that. But when I'm doing the actual math, I prefer to convert that just a tiny bit to saying negative Q lost equals positive Q gained. The negative on the Q lost side will cancel out with the negative inherent to it being Q lost, and we'll end up with a positive number on both sides. That's my preferred way of doing this. And what I've done next is plugged in MC delta T for on either side for each object. So on the Q lost side, the thing losing heat is going to be our copper. So MC delta T for copper, mass of copper, specific heat of copper, change in temperature for copper. We don't know the final, but we do know its initial. And delta T is always final minus initial. So keep that in mind. Then on the right, we've got MC delta T for water. Water mass times water, specific heat, times change in temperature for water. Yes.
Just to make sure I'm following, on the second line, you just multiply both sides by 0.05 and 387, correct? Like the TF, you multiply that by the 120, you multiply the, like you just kind of factor basically?
So this second line?
Yes.
Yes. Next thing I did is I factored these two terms into these. So this is 0.05 times 3.87 times TF. At the time, I wanted to keep as many terms intact as possible so that people copying could see where they were going. But realistically, if you're working this on an assignment, you could be combining these as you go, if you prefer to work that way. But yes, segueing into that, we need to get the TFs out and by themselves. Like I said, this is probably the trickiest version of this type of a question, because we have to deal with the process of getting the TFs out and combined. To do that, you distribute the terms in front of these parentheses into the parentheses, and that's going to give us two constants times TF plus 120 times those same two constants. I went ahead and distributed the negative in as well. Since TF is positive, you multiply by this negative makes a negative. The 120 was negative, multiplying by this negative will make it positive. On the right side, there's no negative out front, which simplifies things. Also, one of our terms is a 1. I didn't feel the need to rewrite that one 3 times if we're just multiplying it. So I simply distributed in TP 4186, excuse me. So that leaves us with 4186 TF minus 21 times 4186. And again, totally fine, totally legal to be combining all of these numbers together in simple terms. In the moment I wrote this, it seemed like a good idea to keep them separate from the notes. Now that the TFs are out of the parentheses, we want to get them both on the same side. And really from here you can do whatever variation of the algebra you want to do. You can move whatever you want to the other side, as long as you eventually get all the TFs on one side. I decided to take this specific term and add it to both sides because that's going to get rid of the negative side. Subsequently, if we take this term and send it to the other side, that'll get rid of its negative sign too. So turn the right into our TF side and the left into the no variable, just numbers side. From there, distribute our TF out, TF times one big constant. The left is also going to turn into one big constant. Our last step is simply to combine and calculate to get our final number. And so, all that finally to say, if you guys can pull out your calculators, what should that final temperature be? 6. Does anyone concur or disagree?
We're at 20.6, but that's-
Yeah, I wouldn't, the only reason I would definitely say something went wrong there is because the final temperature is colder than the starting temperature of the water, which probably wouldn't happen. But we got 21.4, the other, I got some nodding. Do you agree with that number?
I just rounded up to 21.6.
Yeah.
Okay. Yeah, I'm with the rounding and the decimals, I'm flexible there. Our consensus then is it rose a tiny bit over the starting temperature of the water, but not much. Yes.
Would we keep the final temperature just in Celsius?
We can keep it in Celsius. The reason we can is because we plugged Celsius in, and since it's a delta T in the specific heat formula, we can't use Celsius. It just guarantees that whatever we get out for TF will also be Celsius. It's definitely not going to be 21 Kelvin, because that would probably destroy the planet.
So as long as whatever units we use, no problem, and you aren't answering that, as long as it's consistent,
Correct.
and it doesn't ask for a specific unit. Okay.
Web assigned will be specific, but ideally it will be consistently specific. If not, I can usually change it on my end if I need to. So, final temperature, 21.5 roughly, depending on your rounding. And in general, that means that this interaction is heavily favoring the water. There's a lot of reasons for this. First of all being the water has a much higher specific heat. It can literally just absorb all the thermal energy out of that copper and barely change its temperature because of that ludicrously high specific heat. There's also just more water. There's about 20 times more by mass. So that's another reason it can just absorb it, no harm. And no, those are the two reasons. Those are both of the reasons. And it's a good thing that this happens because, again, water is Earth's ultimate heat sink. Without it, the oceans would boil and freeze intermittently between night and day, which wouldn't be good for anyone. I think that's one of the reasons that both Mercury and Venus are just terrible to think about visiting. They have other liquids there that aren't water that do terrible things between night and day. Okay, any questions about calorimetry? Really review for you guys, I understand. The version where we have to find the common final temperatures, again, my least favorite because of the fishing you have to do to get the TFs out and on the same side. But it is the most difficult version that I'm likely to ask you, which is why it's the one that I definitely wanted to make sure was in your notes. Other similar examples might have you know the final temperatures if you're trying to figure out the mass of one object and the specific heat of one object. Because metallurgists who study metals will do that commonly to try to figure out what something is. Heat something up, dunk it in water, figure out what the final temperature is, and work backwards to find the specific heat of the metal and use that to identify it. So any questions about calorimetry before we discuss phase change?
We're not gonna work with like heat capacity.
Specific heat is as far as we're really going to need to go into that right now. As far as this course is concerned, that alone summarizes already the idea that every material reacts to heat differently. And this is the only formula that will come up on your assignments that will utilize anything like that. I suppose we will next week, probably on Monday or Thursday, Tuesday or Thursday, talk about heat conductance, heat conductivity, which similarly there's favorable values for every single element. But that's less its specific heat or heat capacity and more just its raw conductive potential. Related, but distinct. So there will be that, but not specifically heat capacity. There's also another table of constants that we'll look at in a minute, just related to phase change. So there's lots of constants, just not those ones. Don't forget about them, though. If you've already learned about them, they are important. Okay. Now, the sections that the book divides into chapter 11, for the sake of our assignments, are about different processes that happen as a result of thermal energy transferring from one thing to another. And one of the most easily visible things that happens when thermal energy transfers objects is eventually you can induce a phase change, which ultimately is just the result of extreme thermal expansion. A solid object expands so much that it turns into liquid. Now, you've been dealing with these your entire lives, and you've probably done math either the same as or similar to the math we'll be doing momentarily. But before we get there, there's a couple of statements I want to review. A, because they might not make immediate sense, but B, because they do after a minute. So, the statements are: melting is a cooling process, freezing is a warming process, condensing, which is gas to liquid, is a warming process, and boiling is a cooling process. First thing on your minds, do these seem right? No. Your gut instinct, which makes absolute sense, is that, well, if something is melting, it's getting warmer, right? So how is that cooling? If something is freezing, it's getting colder. Which means that these statements only begin to make sense if you think about them in terms of the environment around the object doing the phase change. A pretty classical example in terms of human biology is boiling is a cooling process. The entire reason humans sweat, as disgusting as it is so that there's water on your skin, and as it evaporates, you cool down. That's because for a liquid to evaporate, it has to warm up to its boiling temperature, absorb more thermal energy to actually evaporate, and then once evaporated, it will float away. So it has to keep absorbing thermal energy the entire time to do that, meaning it's taking thermal energy away from its surroundings. And if it's sweat on your skin, the surroundings are you. So as much as being sweaty, I personally really dislike it. It does do its job and technically cools down, which I didn't understand until my upper level physics courses, and I still don't like it, but I deal with it. Similarly, if something is melting, in order to melt, it has to absorb thermal energy from its surroundings, thereby making its surroundings colder, which is what you do when you put ice in your glass to cool down your drink. It absorbs thermal energy from the drink in order to melt into your water. And the reverse is true for freezing. If you put something into your freezer, technically the freezer will get warmer as it absorbs thermal energy out of whatever it is you just put in. Same with condensing. When water vapor condenses on the side of your cold glass, that's technically warming the glass up because it is absorbing thermal energy from the vapor in order for it to condense back down. So things to remember here are to remind yourself of the two terms endothermic and exothermic. Endo meaning in, you absorb heat from your surroundings if you are endothermic. Exo meaning out, you vent heat out into the environment if you are an exothermic process. So that would make boiling and melting endothermic, and freezing and condensing exothermic. There's also, I believe I'm using this right, isothermic, where either temperature stays the same or thermal energy level stays the same. To actually induce the phase change, you need to either absorb enough thermal energy to cause and complete it, or give off enough thermal energy to cause and complete it. Excuse me. The way that we determine how much thermal energy that needs to be is with our good old friends latent heat of fusion and latent heat of vaporization. Just two slight variations of one formula. As has been the case, Q is going to represent heat, thermal energy transfer in or out of something. Uniquely, this formula does not take care of its own negative sign. And most of the other formulas we've been using the past couple of weeks, it has some kind of delta T in it, which will automatically make it negative if you're cooling down. This one doesn't. So we're going to have to remember and assign negatives ourselves based on whether something is absorbing thermal energy for a phase change or venting it for a phase change, which may only frustrate me because I never remember to put the negative sign in until 3 steps later. So, to figure out how to induce a phase change, you need to know the mass of the object and the latent heat of fusion or vaporization, which is another wonderful set of constants that always depend only on what the thing in question is made of. And again, the table will be made available to you. I certainly can't remember them, not even the ones for water, which come up the most. So this is in your notes, it's in the textbook, it'll be provided on all assignments. And mass and this table are the only things that affect how much thermal energy something needs to actually complete its phase change once it's at the correct temperature for it.
What does the L stand for again?
The L is, I suppose, just for the word latent. So these are the variables for LF is latent heat of fusion. Fusion is specifically this. We use this one for any phase change between solid and liquid. So you can put in brackets solid and liquid, solid arrow, liquid, and the reverse arrow. You know what? I'll just no wait, I can't write it. I have something behind here. Fusion, solid, back and forth to liquid, and vaporization, liquid, back and forth to gas.
So for the phase change, you only need the mass and the latent heat of fusion or vaporization, or is there temperature?
There's no temperature in just this part of the formula, because the phase change always under constant pressure always happens at the same temperature. So thankfully this table also lists those temperatures. Let's look, for example, at our good friend water. Melts at 0 degrees Celsius at standard atmospheric pressure. Changing the pressure can adjust these values, but we're going to assume atmospheric pressure for most everything in this class. And once the water is at that temperature, that's the point at which ice and water can coexist. They can both exist at 0 Celsius. What's going to determine what phase it's in is if it loses enough thermal energy to complete its transformation into 0 degrees Celsius ice, or gains enough thermal energy to complete its transformation into 0 degrees Celsius water. The reason temperature is not in the formula is because if this is the melting point, the entire process happens at that temperature. This doesn't change until you're done. Because if you're at 0 Celsius and the ice is melting, any thermal energy added is just going to melt the ice and turn it into 0 degrees Celsius water. So you can keep adding thermal energy, temperature won't go up until it's done melting. Same goes for all of these reactions. When you boil water for noodles, or whatever you might boil water for, tea, once it's up to boiling, it stays at this temperature. It doesn't keep getting hotter. You can put your finger in when it starts boiling. Don't recommend it. And if you put it in, 30 minutes later and there's still water there, it's still at the same temperature until all of it is steam. And as a refresher, you've probably seen this image before, which summarizes this principle. This particular graph, which shows up in every single class that talks about thermal energy, is a energy versus temperature graph, which shows that as you add energy to something, the specific graph is going to be water, ice, or steam. As you add energy to it, it is going to go through phase changes and increase its temperature. When you start at absolute zero, which again, you will never actually interact with unless you are a very specific type of physicist when you grow up. And as you add thermal energy, it will remain solid. It'll just become a warmer solid until you hit that melting point. At that melting point, temperature doesn't change until you add enough energy to finish off melting it. So notice, you keep adding energy, but the temperature levels out until it's completely water. Then adding thermal energy makes it warmer until it hits boiling and it starts to turn into steam. This is one reason why it's very difficult, it's actually impossible, to use MC delta T, or to use rather MCT, to figure out the total thermal energy something possesses, because if it's not a solid, if it's gone through a phase change, it has extra energy in it to have caused the phase change. So you can't use MCT to find the thermal energy level of anything that isn't a solid object. You have to factor in the energy of the phase changes that have occurred to it.
Because it's not shown in the temperature because it used the energy for the actual phase change.
Correct. Similarly, this is the reason why steam is always more dangerous than boiling water, because steam inherently has more thermal energy than boiling water. Steam burns are particularly nasty because if the steam absorbs into your skin, now your skin absorbs thermal energy from the steam as it turns into water, and then you still have 100 degrees Celsius water inside of you. So exercise all caution when cooking really anything.
Okay, wait.
Yes.
So when we're talking about endothermic, exothermic in this class, we're talking about that in the environment, like,
Well, those terms themselves
or the system.
refer to the process within the system. Melting is an endothermic process because whatever is melting has to absorb thermal energy.
But it's cooling for the surroundings because it's taking away the energy, like that.
Right. So these statements up here are from the environment's perspective. These statements are just categorical definitions for whatever the process is. Boiling is always a endothermic process because in order to boil, you have to absorb more thermal energy to complete the boiling. But whether or not you think you're getting warmer or colder depends on whether or not you are the water or the environment. But the boiling is always endothermic. The process is defined as such.
Okay.
So, process definition, perspective. These specifically are from the environment's perspective. So, going through the notes, if you access these online, you will see that the slanted parts of the graph where the temperature is actually rising, you can use MC delta T to examine what's going on in those sections because there's no phase change. We're simply changing an object's temperature as it absorbs or gives off thermal energy. Meanwhile, we have to use our latent heats to examine the flat parts where the phase changes are going on. And like it says on the bottom, in order to go through any phase change question, you have to step through each individual part. If we were looking at everything it takes to get from here to here, we have to look at MC delta T for ice forming, latent heat of fusion for melting, then we add in the MC delta T for warming of the water, then we add in latent heat of vaporization for evaporating, and then we add in MC delta T for steam warming up. Which means these particular types of questions can get a little lengthy, so it's a good thing. I have this written down already. So, as a sample of a similar type of question, a phase change but also calorimetry question, let's look at how many grams of ice it would take to turn an amount of steam back into water. I should section off what part's important or what problem. So everything, this side of the green line is referring to this question. Until we get to here. So as an illustration, some scientists thought it would be a good idea to pump a bunch of steam into a box and then throw in an ice cube. So our before state is we have 0.1 kilogram of steam. Good luck taking the massive steam, but these scientists did it somehow. We have a massive steam at a starting temperature of 115 Celsius, and if someone slid in a ice cube of indeterminate mass, which starts at -6 degrees Celsius. They locked the door and made it a thermally sealed system, and then 2 hours later they came back and we have some amount of 45 degrees Celsius water and nothing else. So the steam is going to have to turn into 45 degrees Celsius water, and the ice is going to have to turn into 45 degrees Celsius water. So our two objects are each going to undergo their own phase change and warming up, cooling down, respectively, as they combine to form one combined massive final product. Listing what we do and don't know. We want mass of ice. We need to know how much ice we need in order to accomplish this particular feat. We're told the mass of the steam is 1 kilograms. Starting temperature of each object, -6 Celsius for the ice, 115 Celsius for the steam. And this is temperature final, not temperature Fahrenheit. Final temperature of both objects combined is 45 Celsius. I've also gone through the tables and listed all of the myriad constants we're going to need here. The ice will melt, which means we need the latent heat of fusion for H2O. The steam is going to condense, so we need the latent heat of vaporization for H2O. That's supposed to be a 6. And since we're dealing with water, steam, and ice as it warms up and cools down, we have our specific heat of water, 4186, steam, 2010, and ice, 2090.
The negative sign is going to end up going on the way, right?
Say again, sorry.
The negative sign on Q lost will end up going away.
Yes, eventually, because the object losing thermal energy is going to be the steam. It's constantly going to be getting colder. And so when we look at all the steps of that interaction, we have the step where the steam has to become 100 Celsius before the phase change can occur. This is eventually going to be a negative term because we're cooling down. Delta T will be negative. Then we lose thermal energy to make the actual phase change occur. We have to sort of put that negative on ourselves since the formula has no mechanism to do that for us. I totally forgot to do that the first time I wrote this down. And then
Why is it negative?
this is negative because okay, I might have got ahead of myself, sorry. This is the way that I like to start. Negative Q lost equals positive Q gained. The negative on this side will cancel out all the negatives inside of Q lost to equalize things. When I start substituting things in for Q lost and Q gained, I opt to keep them positive inside of a bracket, or keep them original inside of a bracket, and I'll apply the negative sign into it later. So within that bracket, before we apply this negative sign, from the perspective of the steam constantly losing thermal energy, it's going to lose thermal energy here, and the negative's taken care of by our delta T. Once it is water, it's going to keep losing thermal energy, and our negative is taken care of by our delta T. In every single question, you need to put a negative on the fusion or vaporization term yourself if that needs to be there, since there's no delta T to put it on there naturally. In this specific question, again, just from the steam's perspective, before we apply any sort of thing, negative sign from out front, from the steam's perspective, it has to lose thermal energy to condense, so we have to put that negative on ourselves.
And 100 minus 115 is 45 minus 100 is just delta T, right?
Correct. I went ahead and put those in to keep from having to write T steam initial minus T final repeatedly. That's just too many subscripts. So that is every single thing that has to happen to the steam to get it into 45 degrees Celsius water. And after we fill in the constants, we can see that we know all the numbers on this side. So eventually we can just turn that into one single giant number. Meanwhile, on the Q gain side, the ice has to go through similar steps in order to end up at the same place. Some mass of ice times specific heat of ice warming up 6 degrees to get to 0 in order to then melt. This is 0 minus negative 6 degrees. We go from negative 6 up to 0. So this delta T is ultimately just going to be positive 6. Meanwhile, we then have to actually absorb enough thermal energy to complete that melting process. So mass of ice times the latent heat of fusion for ice. Then, once we are water, we have to warm up from being 0 degrees Celsius water to being 45 degrees Celsius water. And that's everything going on that side of the equation, every step that the ice goes through. And the one thing we don't know on that side is mass of ice, which is the thing we want ultimately. And on the left, sorry, on the right, every single term has mass of ice in it. So when I look at this, my instinct to avoid having to do it later is to just go ahead and distribute mass ice out and put it there. Does anyone object to me taking that step? Okay, no objections. We'll wrap this problem up quickly. Mass size is the only thing we don't know, so we can start plugging in all of our other numbers here. We know all of these numbers, so we can eventually collapse that down into a single huge number being multiplied by mass ice.
Will this mass be in kilograms?
Yes.
Kilograms?
Kilograms, yes. All of the constants over here are designed to give out kilograms. Same with all of the constants here, which is facilitated by the fact we plugged in the mass of the steam in kilograms. So kilograms on one side should give you kilograms out on the other. and every other constant is designed for those. Eventually, after combining every single term on each side, we'll end up with about 252,000 on the left equals 533,000 times mi on the right. Ultimately then, what should the final mass of ice come out to be?
I got 0.472 per minute.
Correct. 0.472 kilograms, keep that in mind. Mass ice, 0.472 kilograms, which, cosmically speaking, isn't a lot, but that would be just shy of 500 grams of ice, so not insignificant. And I'd say this process does favor the ice over the steam because it does take noticeably more thermal energy to make ice melt than it takes to turn water into steam. And that is sort of a combo of calorimetry and phase change. That's definitely more than enough for today. I told you up a minute after the period ended. Go ahead and be backing up and heading out. You can leave as I'm talking. I just like to ramble. Be working on your homework assignments over the weekend. Send me any questions you have. Tuesday we'll open the floor to any chapter 10 questions you have before that assignment is due, and we will begin finishing chapter 11 on that Tuesday. Let me know if there's any issues you have over the weekend, and have a good weekend. Most important, as well, and have a nice day.
Will the test be online or with an in-person ticket?
I'm planning online through WebAssign, just to give everyone a little more freedom, because you'll have a chance to take it at any point you want within a couple of days. Yes.
Okay, so we did the final answer in kilograms because, like our units over there were already kilograms,
Yes.
degrees Celsius.
Correct.
Okay.
Everything over there is kilograms. Every constant we put in is scaled to kilograms.
Okay, so for instance, if it was like scaled to just grams, then our answer would be in grams.
Yes, if we put grams on this side, I suppose if we plug grams in over here, that would be in every single term, and that would probably make our answer grams. So ultimately, whatever you put in is what you get out,
Okay.
more often than not.
As long as we just keep it constant,
Yes.
right? Okay.
Consistency is key.
Yes, sir. And I was definitely listening. I hope you didn't think I was being rude. But
Oh.
my sister's playing